This is an S3 Trio 3D 2X, and I found this card recently at the scrapyard. I have a little bit of a weakness for S3 cards because, well, I had one in the past, and sometimes when I see a card that looks interesting, I'll take it. Of course, I tested the card when I got home, and I got a post screen that many of you may have seen, but never really questioned it. The problem with some of those S3 cards is that they're just a little bit brighter than a Matrox or a Tseng or an ATI card. So what's going on here? Why are some of these cards so bright? So could this be a faulty S3 chip? I have a few cards that have the same chip, but this card produces the grayish background. This is indicated by this sticker that I put on there. So I tested all my cards. And this is the same graphics chip, the Trio 64V2 DX, but this one is okay. Well, okay, then it's maybe just this chip is bad. Well, I have another example. This is a ViRGE DX. Here is a Diamond Stealth 3D 2000 Pro, and this one here is, well, it just says S3 ViRGE DX 4 megabytes. Again, this one produces the gray background, while this one delivers a perfect black background. You might have heard of the issue that S3 cards are suffering from this brightness bug, but have you ever wondered why it's happening? Okay, and we are posting, but you can see that the background is not really black. There have been attempts to fix this, and there are BIOS patches and ways to correct this in software. But today I want to explore this myself. I want to try to patch the BIOS and fix this bug, which not really was a bug because it originated from a time when we had CRT TVs and the NTSC format, specifically in North America. And the question is, why? Well, if you have seen a TV out connection, it sometimes looks just like this. One cable that connects to your graphics card and you could hook it up to your TV. And this is the composite out or composite video. This is a data connection that sends the entire video output to your TV, which can then process it and show it on the screen. Now, if you know how all CRT monitors work, you know that there is a light beam in there that goes over the entire display many times a second to generate a flicker-free image. That data signal that came over the composite video had to tell the TV jump to the next line. And this was done using a voltage offset. So the signal that arrived had all this information encoded. It told the TV which color should be displayed, when to jump to the next line, and when to jump back to the beginning. So it was just a data stream that was interpreted by the TV to generate a picture. The problem with older TV models or cheaper models was that the data stream had to be formatted in a way that it could easily be interpreted by these devices. And as I said before, there was a specific data pulse that told the TV jump to the next line. And this was basically 0 volts. Unfortunately, the color black was also kind of 0 volts, which means basically the higher the voltage, the brighter the picture or the data pixel that was sent. Now you couldn't go and send 0 volts because the TV would think, okay, I have to jump to the next line. So instead of doing that, they lifted the black color just a little bit by 50 millivolts approximately. So a black color was slightly brighter. And that is what we see in this picture. So this is an offset to make sure that older TV equipment would not get confused between new line and the color black. Now, of course, most of my S3 cards do not have a TV out and do not have a composite connection. But in today's world, when we have LCD monitors and VGA connections, this is very noticeable. It wasn't much of an issue before when we had CRT monitors because they anyway weren't that black. So it wasn't that obvious. Of course, you could argue and say like, okay, just turn the brightness down on your monitor and you will be fine. Yes, that would work, and this is also what many people did back then with their CRT monitors. But the problem is if you, for instance, pair your S3 card with a Voodoo graphics card. That means you had your 2D image, which was brighter, so you turn down the brightness on your monitor. And the moment you go into a 3D game, like let's say Tomb Raider, the game appears darker than it normally should be. So my S3 Trio has this issue, but it's otherwise a really good card. It supports many VISA 2.0 resolutions, By the way, I made a video about Visa 2.0. If you want to watch this video, it's linked in the top right corner where we look into the game Duke Nukem. So these cards are very compatible for MS-DOS and also for Windows 98. So it would be nice if you can figure out why this card is generating this brighter background. And S3 was really good at the time to publish their chip specifications and datasheets. So if you look at this one here, this is the datasheet of the S3 Trio 64V+. And this has over 300 pages with assembly code, with descriptions over registers, and so on. So this is massive. And this allows people to play around with their hardware in a way that is almost not possible in today's world anymore. Now in here, we get direct access to the hardware. And I want to mention, I'm absolutely not an expert. I have only a certain amount of time to prepare for videos like this. However, I think I understood it well enough that I can show you what I found. So the pedestal bit is just a location in the chip that holds either a 1 or a 0. And depending on how it is set, it will either add our offset to make the picture brighter, or it is a 0 and it goes back to regular black. The information we're going to type now into the debug program comes from the datasheet. Let's quickly talk about the architecture, how we can write and read those registers. On S3 cards, there's something called a sequencer. And the sequencer allows us to read or write registers. So we first have to address it and tell it, hey, I want to have access to a specific register. And then you can either read it or write it if you have permission. Yes, these chips check if you have a permission. I'm actually not sure if we need to unlock the chip for reading. So let's try it without unlocking the chip first. So let's start with debug, and we can now write our commands in there. So let's go to our sequencer. This is out. So the out means we are going out from the CPU to another system. And we go to 3C4. This is our sequencer index. And for my chip, I know it is address 27. So we want to go to address 27. Now we can read what is in this address. Now you write I, which is going into the CPU. So we are reading, and we are reading 3C5. This is the data port. So let's read what is on our port. So basically we moved our address to 27 and we are reading now what is on address 27. And I get 27. That doesn't make any sense. Let's unlock our card. 3C5. Now we're writing our unlock key. This is the 06. Now we move our pointer to address 27. So output 3C4 27. And now we read what is on the data port. So we'll access 3C5. This is our data port. We're reading now and we're extracting the information. And we're getting 08. So we had to unlock our chip. There we go. While I did research, I also found other addresses. And this completely depends on your chip. So for instance, I got address 1A. And let's see what's on the data port. 0C. Now, unfortunately, I cannot type 0C in there. I only get C, and you see here in the binary, we have 4 bits, 1100. So maybe one of these 2 bits is our pedestal bit. And the only way to figure this out is if we set it to 0. Is this a good idea? No, because you don't know which bit it is. But for us, we can just try and see if it changes our output at all. So we can try to set these bits to 0 and see what happens. So right now our value is 0C. Now we do writing 3C5. We set it to 00. Let's see what happens. Well, it definitely did something, but unfortunately it didn't change our brightness. So let's see what's in 3C5 now. We have 00 now. So we actually wrote this into our registers. So this is not our pedestal bit. Let's undo this. So out 3C5 and we put 0C back in there. Let's see if it flickers again. No, it didn't. I3C5, it's back to 0C. So these were not the values we were looking for at address 1A. I also got another address, which is address 18. So let's move our pointer 3C4. We're moving a pointer, so we need 3C4. And let's check 18. So let's read what's on the data port. It's 00. So this one doesn't have any values. All bits are 0. That means definitely there is nothing there. Okay, then let's move on to the last address that I got, and this is address 27. So again, out 3C4, this is our sequencer, and we're telling it go to address 27. Okay, and now we can read what's at the data port, and we get 08. Okay, let's use our calculator again. So 0, well, I can put this in there. Let's just ignore it and just go with 8. Oh, look at this. We have just 1 bit set. And to make this 1 bit to 0, well, we just have to override this register with 0. 3C5, and we just set it to 0. Let's see what happens. Our picture changed. And now this is the black that we want. So we found the pedestal bit. This is it. We fixed it. Look at that. We have a very nice dark black. But the problem is that the moment I restart, it is obviously gone. Let's try that. And here it is. We are back at the light black color. So you would have to do this every time you're restarting your system. Obviously, we don't want this. There are ways that you could automate this, but every time you're moving this graphics card out of a system or you're formatting or losing your configuration, you would have to do this over and over again. But if you can fix it in the BIOS, we'll have this issue eliminated forever. You can move the card into another system and will always be black. So for my card, the S3 Trio 64 3D, this is the exact sequence that is required to change the background color from this black-gray to pure black. Okay, let's keep these patterns in mind because they are essential to find where in the BIOS this bit is set. So the first thing we need is the BIOS of the graphics card. And I'm using NSSI because this allows us to easily dump the BIOS. You can go to Tools, Save Video BIOS, and we can call it Trio 3D patch. So now we have a Trio 3D patch.vbi file on our system. And now I'll use hue to jump over our BIOS file. So I still have this here. This is a setup I created for patching a 486 BIOS. There were fake cache chips soldered to the board, and the people who created this deception made sure that the BIOS always reported that you have a cache on board. I think it was 256 kilobytes. So if you do like these type of modifications and hacking, well, maybe watch this video if you haven't already done so. It's linked in the top right corner. Okay, the first thing we need to do, we need to change the mode, and we want to go to decode. So here is our BIOS. By the way, 55AA is the marker for BIOS files as far as I understand. I think this is a 32 kilobyte BIOS. So we should go until 7FFF. This should be our last entry. And yes, this is the end of the file. This is our checksum here. The 8B is our checksum. Okay, so now we have a lot of stuff here, which doesn't say much, to be honest, and I highly doubt that anybody is going to run through this manually. So we should use the clues that we got while trying to set our pedestal bit. And these are mostly the hexadecimal numbers that we have seen, for instance, 3C4 and 3C5, and also the 27, the address, because this remains the same. So these values should appear again. So if we see these hexadecimals somewhere close to each other, this is most likely what we're looking for. So let's search and just search our file a little bit, and we're looking for hexadecimals. Let's look for 27 because this was the address we told the sequencer to write to. So let's see if we can find 27. I'm afraid that we'll find many of those, but let's just see. So this is not an address. So this address should be moved into a register. Let's ignore this and move on to look for more 27. This is also nothing. Sometimes the decoding of hue is not 100% correct, so it is going to be a little bit tricky. This is also not it. What do we have here? No. Let's just continue. Oh, here we're moving. This one here might be interesting. Oh, and look at this, what we have 2 lines above. Look to the very right, 03C4. Then there is a call, and then we are putting 27 into a register, AL. Then there's another call, and here we set 08. And this is actually the value that we got when we read our data port, remember? we got 08. So this looks very close. All the pattern matches up. Everything is here. We have the 27, we have the 08, and we have the 03C4. So let's just see where is our chip unlocked. Our S3 Trio chip needs to be unlocked before we can write at address 27. So let's just quickly look at this call. It might just be our chip unlock. Let's figure that out. So 19E4, 19E4. So again, we have this pattern where we see 03C4. Oh, well, you can see here 08, which is also the first thing that we did. We called 3C4 at address 8. This was our sequencer address. And look what's happening here. We are moving the value 06. So yes, we definitely unlock the chip here and then we return. Great. So I think we found everything that we looked for. This is the method that unlocks the chip. And then it does some additional things, but then we get to this value. This looks so much like the data that we explored using the debug application. So this is our value that most likely we just have to change. And we know that it's only 1 bit. We saw that in the calculator before. So we can just set this to 0. Now we need to keep in mind what we're changing because we have to update the checksum at the end of the file. So yeah, let's just change this and set this to 0. That's it. Now the only thing that we have to do is to change the checksum. Okay, now we have to figure out what to do with our checksum byte, because if this is not correct, the VGA BIOS will not load at all. And how this checksum byte works also stumbled me a little bit, but it's quite easy once you understand what's going on. So what is happening is the system or the CPU adds all bytes excluding the checksum byte together in an 8-bit addition. So it just adds all bytes together. Let's say there's another 155 plus 92 plus D4 plus 8C. Okay, now I have 2D2. The value that we would get is D2 for our calculation. And now we need to add something to this value to get 00. Let's take D2. Now, if we want to get D2 plus the checksum to 00, we should essentially end up with 100 because only these two would be considered. And if it's 00, that means the checksum is correct and the entire BIOS is correct. So how much do we have to add to D2 to get to 00 or to 100? So our checksum would have been 2E. In our case, we have 8B. What we did was we reduced the values of our bytes by 8 because we changed an 8 to 0, which means we have to add 8 to our checksum. Why? Because the bytes of our code got lighter by 8. And this is super easy now. We just have to add 8 to our checksum. And this is 93. This is how the checksum works. I hope I could explain this. Basically, if we make the code lighter, we have to add something to our checksum. Because in the end, these two values are added together and they should be 00. And this is it. I will program now another EEPROM chip. What we should see with a new BIOS is that the background should be black immediately when we power on the system. So this is a permanent BIOS fix for this card. Let's see if it works. So let's get this old chip off. I will keep it. And here is our patched BIOS on it. Hopefully now, when we boot with this card, it is going to show us the black background immediately from the moment we post. Moment of truth. And I think this is fixed. Yes, look at this. We have a deep black background. No longer any washed out colors or the light gray background. Wow, I think this worked. It's maybe difficult to see. I'll definitely put a side-by-side comparison here right now, how it was before and how it is now. But before I go, I want to check one more time what is now at address 27 in our sequencer. So the first thing we have to do is we have to unlock the chip. And now we can move to address 27. This is where our pedestal bit is living. Let's read what is on the data bus. And it's 00. So here it is. We fixed it in the BIOS, we flashed it, And now this card no longer has the brightness bug. And this is all I have for you today. I hope you enjoyed it. If you did, please give this video a like and subscribe to my channel if you haven't already done so. Let me know in the comments if you're going to attempt this, and of course if you were successful. I'm really curious if some of you will try that. Also, a big thanks to all my Patreons and the people supporting this channel here on YouTube. If you want to support this channel, you can become a member here on YouTube or head over to Patreon. And I hope I will see you in my future videos. Take care and bye bye.